application. All right, so problem 2. Application. This is not going to be pretty because it's an application. We're considering the population of white-tailed deer in the state of Kentucky. The Kentucky Department of Fish and Wildlife Resources sets guidelines for hunting and fishing. Before the hunting season in 2004, the population is 900,000 in the whole of state. The deer population, if the deer population has plenty to eat and is not hunted by humans or other predators, it will double every 3 years. Okay, so that's from like research. That probably would not be hard to demonstrate, but okay. So the Kentucky Department of Fish and Wildlife Resources reports that the deer population densities for 32 counties in Kentucky, the average of which is approximately 27 deer per square mile. 27 deer per square mile. Suppose this is the deer density for the whole state. So the carrying capacity for Kentucky is 1,072,764 deer. Okay. So we have our birth rate, because it doubles every 3 years. We have our initial population, and we have our carrying capacity. All right. So for this application, these are, but you can, if something doubles in 3 years, R is ln of 2 divided by 3. Remember, that's how you figure out. If you know the doubling time, you can figure out the growth rate. So it's 0.2311. So these are my conditions, P sub naught, K, R. Substitute this value into the equation and form the initial value problem. That's the first thing they want us to do. Then solve the initial value problem, and then they want to know what the population will be in 3 years. Okay. All right, so this is my initial value problem. dp dt equals R times P, or 2,311 10,000ths times P times 1 minus P divided by 1,072,764, and P naught is 900,000. So I did that. I'm going to try to solve this, but remember, I already solved an initial value. Remember, I already solved a logistic differential equation, right? This is the solution. So what I'm going to do is I'm going to just piece together the solution based on this. So this is my solution. And then this is K minus Y sub naught divided by Y sub naught. All right. So if you graph the solution, this is the logistic curve. If it starts right at 900,000, this is what it looks like. This is what a logistic curve looks like. Logistic curves looks like an S curve. So it's growth that gets tempered. And then the asymptote, right, asymptotic behavior, if you look at this, as x approaches infinity, P approaches the carrying capacity. P approaches the carrying capacity. Okay. And then negative infinity, it approaches 0 in this case. Okay. And then just to give you a comparison, this is the logistic model. I got this out of the book. That's why instead of trying to reproduce these pictures, I just snipped the photos. This is a comparison of what would happen if exponential growth, okay? So eventually deer would rule the world if nobody hunted them, I guess. So this is exponential growth compared to a logistic growth, the S curve. Okay. And then what would happen in 3 years? Well, remember, we said without any tempering of the population in 3 years, something double, the population of deer would double. But if you do temper it with the carrying capacity, P of 3 equals 978,830 deer. So this is far short of doubling, right? So doubling time is based on the assumption that there is nothing tempering the population growth. Okay, all right. So this is an application of logistic differential. All right, we're gonna look at the slope field for the logistic differential equation. I used the solved by using that website I told you about, guys. It's really nice. So if you notice, there's two equilibrium solutions, right? There's equilibrium solution is a spot where the derivative is 0, where the solution is a constant function. So in this case, it happens at, if you see, this is 1,000,000, this is 1,250,000. So the one in between is the value of K. And we did say it's stable. And look, all the slope, all the curves approach K. And then obviously 0, we said it's unstable. So the problem we're solving basically is kind of a Noah's Ark scenario, right? If you have at least two of the species, it's assuming it can survive go to the carrying capacity. When in reality, I have an interesting, just one homework problem for you. In reality, that's not true. You need, right? That's why there's something called threshold population. So I'll let you. So there should be, if this was even more realistic, there should be a steady state solution in between. But this is just some solutions drawn in. This always looks kind of cool. So where's our solution? Wait, what was our initial population? 90,000, right? 900,000. So we were right here somewhere. We're right here somewhere. Okay, but okay, here we go. They might take longer, right? So the closer they are to zero, the longer they would take to reach the carrying capacity. All right. Okay, so that's the application. If you want to kind of the logistic. So this is a wiki page on the logistic differential equation. So the terminology is pretty standard. It was actually written down by a person. Okay, it's the Verhulst, Pierre-François Verhulst. It's not named after him, surprisingly, but so the Wikipedia article is kind of interesting. It basically talks about how people were a little obsessed with human population getting too big and basically us not being able to survive on Earth. So people were worried about some sort of a warfare. If you remember from history class, this Thomas Malthus guy predicted some pretty grim future for humanity as population growth, and he was of course incorrect because he didn't count on human ingenuity. But so after he published this book, an essay on the principle of population, a lot of people became interested in population growth. So they studied like animals and different species and so on, bacteria. And so this guy formulated this logistic differential equation, which is still used today, but of course in a slightly modified form. And then this talks about how people quote unquote rediscovered it in his writing. And this Lotka, you'll see this name a lot if you study differential equations. You'll see this name a lot. He did a lot of work with differential equations. So American scientist, I think. Okay, so anyway, this is a wiki article on the logistic population growth and its history. So it came into being after people started to worry that too many people will live on Earth. All right, and then I also mentioned R and K selection from biology. So R and K selection are the two. Actually, R and K selection is a spectrum. Is a spectrum of selection strategies for species. So R selection is not relying on the environment. I hope I'm saying this right. So R selection is not is a selection strategy where you don't rely on the environment to sustain your young in order to be able to reproduce themselves. So what you do is like so the number of offspring is high, parental care is low. Ouch. So you move on to like the next offsprings. Reproductive maturity is early, size of offspring small, and so on, right? So this is like sea horses or something. That's what I'm picturing right now as the early mortality. And then K is us, right? K selection is us. We're counting on the environment. So we're counting on that there's a carrying capacity. So like elephants and so on, humans. So the number of offspring is low, the parental care is high, their reproductive maturity is late. So our offspring are, in biology, the term expensive is used. Like it actually, you expand a lot of energy to produce offspring. But what we're counting on is that they will survive and will themselves produce offspring, right? So K selection. And then it's R selection and K selection is a spectrum. It's a spectrum somewhere in between, right? Okay, so they're just two terms from biology. All right. I do have a little homework assignment for you. It basically just adds one little element to this, one level of complexity, okay? And then if you study this in college, there's a lot more interesting things to study. The applications there's many, like tumor growth. The logistic differential equation in one formulation is used to describe tumor growth as well. And then if you want to study more than one species, you have to do systems. All right. And I'm also going to attach a few resources for you guys, okay? If you want to learn about ODEs, and I have a programming resource too, if you want to learn how to program over the summer or something. All right.